All right, so yesterday we left off with this slide right here, kinda. We worked some problems, but remember, I told you there was two different ways to look at thermo reactions versus equilibrium reactions. And you can do three things, two reactions, and in thermo, you do one set of rules, and in equilibrium, you do another set of rules. And I get it. It's a pain in the butt, and I hate it, and it's frustrating to know both sets of rules for two different things. But the only way to remember them is to practice them. So if we're looking at thermo rules, remember, this is summation. So I guess this is really, I probably should have included this. This is summation rules. Okay, so these are the things you'll do when you have a bunch of different steps. Now, what do we call those many steps that make up a whole reaction? That M word? A mechanism. So these are really for mechanisms, okay? So if you flip the reaction, what do you do to the sign of delta H? Flip the sign. So it can go from endo to exo or vice versa. If you change the coefficients, how do you affect delta H? Multiply or divide, okay? And then finally, what happens if you need the total value of the delta H? You add them all up. And this is different if you need the total K because you multiply the K's. And so there are some differences. To me, the thermo rules are easier because it makes sense. The ones that are the equilibrium rules are a little bit different because if you flip the reaction, you take the reciprocal of K, which is aggravating. With delta H, you just flip the sign, which is a lot easier. You don't have to do any calculations. Okay, so we worked those two types of problems, and so here is the one we left off on, correct? Yes? Yes, no? Yes, okay. All right, so what I want to do is I want to work this problem. So first of all, how many mechanism parts are there to this reaction? There's three parts. And down here at the very bottom is our goal equation. So notice what we want as our reactant. We want one thing as our reactant. Is that reactant in one of our mechanism steps? Which step is it in? The first step. Now let me ask you something. Is the reactant in the goal equation a reactant in mechanism 1? So do we need to leave that one alone? Can we flip this at all? No, we can't flip it. But is there something that's different about the mechanism step versus the goal step? There's the coefficient. Very good. So in the mechanism part, there's, well, you can't see that. There's nothing there, but in the goal, can't really see that either. So what do you think we're going to have to do to that top one? Multiply what by 2? Everything by 2. So we're going to come in, we're going to put a 2 here. Yep, let's go ahead and do that. We're going to put a 2 here. We're going to put a 2 here. And how is that going to change our delta H? Multiply by 2. So it's going to turn into negative 0.04. We good so far? Okay. Now, we're finished with our reactants, right? Because there's only one. So now let's look at our products. So we've got B2O3 solid and 3 waters. So let's look at the B2O3 first. Is it already in the place that it needs to be? Are they both products? But is there something else that's wrong with it? The coefficient's wrong. So what do you think we need to do to this bottom one? Half it. Very good. So what we're going to do is we're going to take that and make it a 1. Take that and make it a 1. And what happens to the water? Very good. It turns into a 1/2 right there. So I guess I'm write this in pink so it stays the same. So if we change the coefficients, how does that affect our delta H? Halves it. So what is half of 17.5? Okay, we good so far? Now we've got this thing in the middle that's going to be aggravating to us. No, something doesn't look right. No, because the H2B407 won't cancel, will it? What is... Oh, I know what it is. It's a typo. Here's the issue right here. Do me a favor. I forgot to change this from last year. Right here, there needs to be an H2. That's my mistake. Right here in the third step of the mechanism, the reactant, it's H2 B407. Now do you see that there is a possibility of it canceling? Okay. No, just add the H2 in there. Does that make sense? Exactly. So say that one more time. You can't cancel them. Why? They're on the same side. But what did we already establish about mechanism step 1 and mechanism step 3? Can you flip those in any way? Because if you flip them, that's going to mess up your goal equation, right? Well, if I need to cancel this H2B407, what am I going to have to do to this middle step? I'm going to have to flip it, right? So, mentally, can you flip that? Yes. So here's what we're going to do. We're going to come in, and we're going to now cancel that. And yeah, hold on. There's one other thing we got to do. Third one, first product. What about it? Say that one more time. Why am I going blank? No. Because when you flip it, you have 2 plus a half, which is what? 4. No, 3. And that gets you your 3 waters. But the problem I'm having is this thing. Hold that thought. No, we're going to get it right. We're going to get it right. The first step. So look at the first step of the mechanism. Do you see how we doubled it? Here's the problem. I'm going to erase this. If you double it, look at right here and look right here. Do we need to get rid of both of those? Yes. So something is now got to happen again. So what are we going to have to do to that top reaction again? Double it again. So it's, again, just stay with me. So this is going to change to 4. This is going to change to 4. This is going to change to 4. And this is going to change to negative 0.08. Just stay with me. I promise it'll make sense. Now, can we cancel out that HBO2? Yep. All right. So now we can cancel this. We can cancel this. But what do we have to do to this middle step? We had to flip it. So if you flip the reaction, what do you do? Flip that sign. You with me? Because to get this, like, you see how they're on both the product side? Well, we need it on the reactant side to cancel it. Yep. So not only does that cancel, what else cancels? This cancels and that cancels. Does that make sense? Yep. So let's do this. So now let's sum the entire thing up of what we have. So I've got 4. Let me do a different color. Does that stand out a little bit better? Yes. So all I did was just bring down everything we had left. That's where I was heading next. So technically, how many H2Os do I have? Why do I have 6 written down? I hate this problem so bad. Alright, you know what? I've wasted all this time now. Because I hate this problem. There's so much you got to do to it. Alright. Yeah, let's go back. I apologize. I absolutely despise this problem. Just because... No, because the way it's set up, it's not going to work right. Yes. Yes. We're trying to. All right. Do you see how all three of these are set up in steps? We're trying to make it look like this thing. Well, each step has its own delta H. We're trying to solve for the total delta H. Okay. Yes, we're trying to get steps in order to make it. All right. So let's actually do the worksheet that I gave y'all. If y'all will look at this sheet right here, it's on the back. These are a little bit better practice problems. It's this one right here. Yeah, we're going. All right, so this is the sheet we're going to work on now. So calculate the standard enthalpy change, delta H, for the formation of 1 mole of strontium carbonate, the material that gives the red color in fireworks, from its elements, okay? And so here is our goal reaction. It's right. It's the top. And then we've got 3 different mechanisms part to it. So the first thing we need to figure out is how we can get all of these reactions to be correct. Yes, sir. Jake. Okay. All right. So the first thing is, let's look at our reactants. So we've got SR is a reactant. Is SR a reactant in one of our mechanism steps? Okay. Right there, we're good. All right, we've got graphite as a reactant. Is graphite already a reactant in one of our steps? Yes. It's in step 3. All right, we've got 3 O2s to deal with. We'll kind of get to that in just a second. And then finally, we've got strontium carbonate as a product. Is it already a product? Yes. So do you agree that those 3 things have to be locked into place? Now the good news is, are we going to be flipping any of these reactions? No, because they're all locked into place on the right, in the correct locations. Okay. Now the next thing we need to look at are the coefficients. Is there any coefficient in the goal for strontium? Nope, there's not one of the mechanisms, so no coefficients. Graphite, we're 1 and 1, we're good. Strontium carbonate, we're good, so we don't have any multiplication or division to do. The weird one is this thing. Okay, and we'll come back to that in just a second. So now let's look at our mechanisms to see if there's anything we can cancel out or cross off. Remember, you can cancel like terms on opposite sides of the arrow. So is there anything we can cancel from step 1 to step 2? All right, so strontium oxide, we're going to get rid of that. What about 2 to 3? All right, we're going to cancel that. So the problem is now, we know what we're left with SR. We know we're left with C. We know we're left with SrCO3. But what about the oxygen? You've got there, and you've got there. Very good. So 1 plus 1 is, or excuse me, a half plus 1 is 3/2 O2. So this one was pretty straightforward, pretty easy, right? Nothing too difficult, nothing too hard about that one. Potentially, there may be some of them that are like that. So what do we do to all of our delta H's? Add them all up. So 8, so that's going to be 0. 18, 21, 22, and then we've got 5, 10, and 12. So negative 12, 20. Is that right? Okay. Now, we're solving for the delta H of the reaction, right? So delta H of formation is going to be negative 1220 what? Per mole of reaction. Because go back up and look at the question. And again, it's all these numbers are going to move, but I'll come back to it. It says calculate the standard enthalpy change of the formation. So it's delta HF for formation. F2. It's a not symbol, yeah. And Devin, why did I put the not here? Because look at all of those. What do they all have? They've all got knots. So if it's got a knot, bring it down. All right, you guys do number 2. See if you can figure out number 2. Hopefully this was a little bit more challenging. All right, so again, the first thing that I would always do is try to lock things into place. And if you can't lock it, then you got to move it around. So I'm going to start with this. So the first thing I'm going to notice is I've got 2 carbon solids. It's in the reactant location. Is it in a reactant anywhere else? Which step? Step 1. So I know it's going to be locked into place. So can I flip this one? Okay, let's look at water. Now, water is always one of those weird ones, so we're just going to ignore it for just a second. So we're going to move on to methane. Is methane in the product side in our mechanism? No. So automatically, what do we have to do to this to number 3? Flip it. We already got to flip it. So here's what I'm going to do. Because I've got enough space, I'm going to rewrite it. I'm going to rewrite the CO plus 3H2 yields CH4 plus H2O. Okay. Now I've got it locked into place. It can't go anywhere. And the last reactant is carbon dioxide. Is it already on the product side? Which step? Step 2. All right. So it's locked into place. So I can't flip any more of them, right? There's no more flipping going to be going on. Now let's go back and let's look at the coefficients. Well, again, let's always leave water and oxygen, all those common ones out. What's wrong with the coefficient of the first one? It's a 2. So what do you think? What am I going to have to do to the coefficients? Which one? The first one. So I'm going to put a 2 here. I'm going to put a 2 here. I'm going to put a 2 here. A 2 here. And then what do I do to the delta H? Double it. So what's the total? Very good. 262.6. So that's my new delta H for that reaction. Forgot. Oh, thank you. I'm so glad you said that. So since I flipped the bottom reaction, what do I have to do to it? Got to make it negative. And like I said, if I ever flip a number, I always like to write the word flip. That way I know that I did it. I don't have to question myself on it. Okay? All right, so now we've got all our coefficients looking happy because we've got one carbon dioxide, one methane. So now we just need to start canceling some things off. So I've got 2 COs in mechanism 1, but then I've only got 1 CO in mechanism 2. Very good. You can't just go 1 to 2. You notice how you got to use all 3 of them? So right here, how many carbon monoxides do you have? You've got 2 of them. So those 2 will cancel those 2. Sarah, now do you see what I mean by you use the entire side versus the other side? So that's kind of what I was referring to there. Okay? It is on opposite sides. Not different mechanisms, sides of the arrow. Because these 2 that are in the orange circle are on the reactant side of that arrow. So you can use them together. You with me? You see what I'm saying? Now, let's look at our hydrogens. In mechanism step number 3, how many hydrogens do you have as a reactant? You've got 3 of them. But the problem is, notice what you got sitting right here. How many do you have right there? You've got 3. So what can you do with those 3 products versus the 3 reactants? Cancel. So I can get rid of those, and I can get rid of those. Okay, does that make sense? All right, then the last thing. Now here's the weird one. I'm going to change colors on this one. I'm going to change this to green. I've got 3 waters as a reactant, and I've got 1 water as a product. So what am I net left with? 2 waters. So basically that one will cancel, and that one will cancel. And how many did I want to be left with? I want to be left with 2. How many am I left with? With 2. Does that make sense? So, if you bring it all down, I've got this left, I've got this left, I've got that left, and I've got that left. Everything in red. Is that exactly what you wanted out of your goal equation? Yep. Okay. But we only did 2 things to our delta H's. We doubled one and flipped one. So, now you just add them all up. So what would be the delta H of this entire reaction? It's going to be positive something. Is that right? So it's 245. So 245.3. So it's going to be 0.3, 245. So 7. So it'll be 17.3, right? Wow, what am I doing? That's right. Because 7, 12, 5, yeah, so it's 15.3. Positive 15.3. No. How did you not? I mean, that's simple addition. 262.2 plus negative 41.2, or subtract, either way. You had to double 131.3. Determine the standard enthalpy change. No, this is just the reaction. Delta H reaction not. Now, the reason why it's not delta HF is because if you go back and look at the past one, we formed one thing. This is just a combination of several things. So it's just a reaction. Come here. Come here. Come here. All right, watch. Let's do this together. So 262.6 minus 41.2 equals minus 206.3 equals 15.1.
No, still not 15.3.
Do what? Did I? I put the wrong number in? And I did it wrong? Is it 20? Did I put in 206.1? 206.3. Oh, okay. Well, see, I am right. I put in the wrong numbers. Because it's 206.1. All right, so we're good there. So let's move on to the next topic. Guys, remember at the very beginning I told you there were 5 ways to calculate delta H. This is the 5th and final way. It is the most difficult and it is the most missed because there is a lot of numbers, a lot of calculation, and a lot of counting going on. And also, this is the backwards equation. So do me a favor right here. Write the word backwards and put a star, highlight it, underline it. This is going to be backwards from everything that we've done. And you'll see why it's backwards in just a second. Huh? Yes, we're all back in the notes. Okay. So, bond energies. But energy must be added to do what? To break bonds. Okay. So, if it's breaking bonds, that's an endothermic process. Why are we adding energy specifically on the molecular and crystal level to break these bonds? What are we doing? Read that red part. Overcoming the Coulombic attraction of shared electrons. Now, real quick, let me ask you something. When it says the word shared electrons, what type of bond is that? That's covalent. And what's that word that when you hear covalent bonds is always that other word? Molecule. Very good. If you say something enough, people will eventually remember it. Okay? Covalent molecules. Covalent molecules. So, we're talking about molecules here. Energy is released when bonds are formed. Okay? That's exothermic reactions. Now, going back way long time ago, why do atoms make bonds? There's 2 reasons. Yes, but that's not the word. I need one word. Stable and lower potential energy. Okay? Those 2 reasons. So, because the resultant Coulombic attraction between the bonded causes lower potential energy, causing a release. So, they're excited about it, right? So, again, if you had to be an only child and do all the chores all the time by yourself, you would hate that. But if you had a sibling to split them up with, that's what's going on there. This is a giant misconception among students. So once again, it takes energy to break, and energy is released when bonds are formed. So here's why it is backwards. Delta H is, again, this is bond energies. Delta H is the sum of the energies required to break bonds. What does that mean? That is endothermic, correct? Positive signs, since energy is added. So it's the sum of the bonds, the energy required to break a bonds, plus the sum of the energies released in the formation of new bonds, which is all going to be what signs? Negatives. No, we never did this. Okay? So this is backwards from the normal thought. It's reactants See, I already got it backwards in my head. Write this. Is that right? No, I was right in the first place. See, I get it backwards in my brain too. So it's reactants minus products. Why is this different from normal? Because it's normally products minus reactants. That's why this is the most missed part, is because people forget to swap these around. So it's the bonds that are broken minus the bonds that are formed. That is why this is so weird in doing this. So let's look at a problem. All right. So using bond energies, this is going to be the key word that's going to clue you in. Bond energies. Calculate the change in energy that accompanies the following reaction. Okay? So we've got H2 plus F2 going to 2 HFs. Now, another way you can determine that it's bond energies is if you see this stuff. Okay? Are you with me so far? So let's rewrite this reaction a little bit different. So we have H2 plus F2. What is in H2? What type of bond do you have there? Okay, you've got H, right? Plus, what is in an F2 bond? F to F. And that is going to yield an HF, right? So, the way we're going to write this is HF, HF. Very good. Why did I write it twice? The coefficient of 2. But again, this is backwards from normal. Which side up here has to be broken? So these are all going to be broken. Okay, what about those over there? These are going to be formed. Does that make sense? So when we do our math, we're going to need an HH plus an FF minus 2 HF bonds. Now do we have numbers to plug into this thing? It's the same thing, but it's backwards. And again, I keep saying that because I want you to understand what's going on here. So here's the deal. So we've got, I'm going to do it in white. We've got 432 plus 154 minus 2 times here's the part where everyone always messes this part up. This next part's always what happens. It's negative. Why is this 565 negative? Very good. These are going to be your exothermic reactions, so you have to flip it to negative 565. How did I know it was negative? Because remember, when bonds are formed, energy is released. Therefore, it's exothermic. Are those HF bonds being formed? Okay. So, and again, another way you can think about this is that this is exo. Therefore, that number must be what? Negative. Over here, these are broken. This must be endo. Therefore, these numbers must be positive. Again, it's tricky. Because products are always formed. Now I need a little bit of help with calculations. Does somebody mind helping me with those numbers? Not you? Just go ahead and give me the whole answer. So 586 minus negative 565 times 2. So it's going to be plus a pot. So it's going to be oh. I'm glad y'all are doing it in your head because I don't feel like doing all those numbers in my head. Oh, because, yep, it's plus. Yep, 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 yep. Okay. What do you mean? Yeah. You're right. And I guess that's what that previous slide was getting at. It's the numbers plus. I agree with you. I've never thought about it that way. You're right. All right, so what's the answer? 17 what? Positive or negative? Positive. So, positive 1716 kilojoules per mole of reaction. So is this an endothermic reaction or exothermic? It's endo. Is it spontaneous or non-spontaneous? Non-spontaneous. So does hydrogen and fluorine naturally just react to create hydrogen fluoride? No, we know that. Otherwise, there'd be a bunch of hydrogen fluoride floating around in the air. But do you agree it takes a lot of energy to make those two things come together? Yes. Okay, so that should be mentally kind of where you sit with this as well. So let's look at one more example. Everybody got this? Okay. It's going to be a little bit more challenging. Okay. In the Krebs cycle. Right? What is the Krebs cycle used for? It's part of photosynthesis. Fumaric acid is hydrated to malic acid. Calculate the heat of reaction in kilojoules per mole using the appropriate bond energies and the reaction shown below. And this is why this is a challenging process, because we've got to take this part, oh crap, or I can just show you the answer. We've got to take this part and convert it to that part. Okay? So what has been chemically and molecularly altered from the first one to the second? Let's look at the easy one first. Water's been broken, right? Yes? Do you agree that all of these things are going to be broken? Now, in a water, what types of bonds are there? Come on, it's a simple answer. OH bonds. Duh. How many OH bonds are broken in water? 2. So we've got 2 H bonds broken, right? You cool with that? Now, to get from this strange fumaric acid over here, do you see any other things that look like they've been altered? So we're good there. We're good. All right, so this bond checks, right? That bond checks. That bond. But this one does not. So what was broken? Okay, so we had one CC double bond. Do you agree? All right. So this bond checks. This bond checks. That one checks. That one checks. And that one checks. So was there anything else that was broken? No. This is it. Does that make sense? We cool with that? Yes, no, maybe? Sarah? Come on. I don't want to go any farther until this makes sense. Do you agree that 2 OH bonds are broken in water? Okay? So then, all of these other things check out except from here to here, it changed. It went from a double to a single. So that's what was broken. Okay? So now, what we can do is we can plug numbers in. So it's 2 times. How much energy does one OH bond take? Okay? So we've got 463. And how much does one CC bond make? Yeah, it's 839. CC double. No, that's a triple bond. It is 614. right? So then we would have to do those. Anybody got that in your brain? Thank you. 926. So this is the amount of energy required to break something. Oh. I'm just relying on you guys. I don't do 15 what? Thank you. Okay. All right, over here. So in terms of what was formed, so we broke two carbon-carbon. We broke a carbon-carbon double, but what did we form? All right. So again, these are formed. So we form one CC bond, one single bond carbon-carbon. We formed one carbon-hydrogen bond. We also formed one carbon-oxygen bond. And anything else? One OH bond. Does that make sense? Okay, so that was formed, this was formed, this was formed, and this was formed. So now we just need numbers. What's wrong? I told you that this is the most challenging. This is the one that's the most difficult to do. So what is one CC bond? All right, so 1 times 348. No, 48. 1 and 1 carbon-hydrogen bond, 413. 1 CO bond, 358. And then 1 OH bond is 463. Yep, you just figured out what was broken and what was formed. Plug all the numbers in and go. It just takes time. What'd you get? Sarah, did you get a number on this? Okay. But you should know how to do those sheets tomorrow.